All right, so continuing on with class 14, we're going to do this example out of our book, Bornacki, where we have the steady state process, and we're going to do a heat exchanger. I can't find my cursor. Let's see. I want to point out again that we have things like this right here. They're not showing. I guess maybe this is probably a good one. This first stage heater right here is a heat exchanger, right? Where we have, here's feed water coming through here, and then here's a bleed steam coming out of there and then draining out, right? So we have two inputs and two outputs in a heat exchanger. And that's our purpose in doing this problem right here. Let's see what the example says. In this case, is refrigeration. So this is definitely in every refrigeration plant. There is going to be a condenser. It's not always water cooled. Sometimes air cooled, but this is water cooled. And it's a large refrigeration system. They're using R134A. It's the refrigerant, and it enters the condenser at 1 megapascal. And 60 degrees Celsius right there, right? So this is the vapor coming in, right? Good chance that it has been compressed by a compressor. And now what we want to do is we want to remove some heat out of it, right? And we want to turn it into liquid. This is a very common thing that we need to do. And something, one of the properties of refrigerant is that we can remove the latent heat of vaporization so that it changes from a vapor into a liquid, right? And doing that, we remove a lot of heat because there's not just reducing the temperature, it's reducing the phase. And that's the latent heat of vaporization. It's a large amount of heat where it actually stays the same temperature and pressure for quite a while until you've removed enough heat, right? So underneath the vapor dome, and it doesn't matter what diagram, as long as the diagram has the vapor dome, the vaporization that goes between here. So a lot of times we will have an enthalpy versus you can have a specific volume, but most of the time it's actually versus entropy. Well, I'm sorry, I shouldn't say that. It's not most of the time, but a lot of times we will use one which would be an HS diagram. We haven't done entropy yet, but anyway, this right here will represent the latent heat of vaporization coming in between there. Did I say that correctly? I think so. So anyway, continuing on. So they give us the flow rate of the refrigerant. That's good. And then they give what it exits at these conditions. So we have inlet conditions, outlet conditions, and flow. These are the important things that we need to know as it flows through and then down and out. And now the cooling water, it enters at 10 degrees right here, and then it exits at 20 degrees. And we want to find the rate, determine the rate at which cooling water flows through there. So we want to get the mass flow of the water. Very classic problem. Noteworthy, you can make this into a bunch of different problems. So just be aware of that. So coming back to this in here. So this is a very common heat exchanger application. I don't know if I need to redraw this. I probably will anyway. So I'm going to redraw this thing. And which way do they draw it? Which one has tubes? Okay, see, so what they're doing is this sort of like a header right here going across where it kind of like splits, comes in, and then it goes through a bunch of tubes, and then there's another header right here where it all comes back together and then comes out. That's just one configuration of a heat exchanger. But you could say that this is, and this is the mass of the water flowing in. So I'm going to go TWTR, comma 1. And I'm not going to number them this time, I guess. Yeah, I'm not going to. So you're going to go, so this is TWTR2. And then we have a flow, and a lot of times you'll learn all about this in heat transfer. But there's like counter flow, like this is flowing in this direction, so you want this to flow. There might even be like a little baffle or a series of baffles as this thing comes in. I drew that wrong. And has to go around it has to go back and forth around the tubes right in there to get in. All right, come on. Yeah, he's not. There you go. And anyway, so we have an M dot of what am I going to call it? Refrigerant. I don't know if I called it any. I guess I called it R, and then I called that 1. Not 1 because it's the same mass flow all the way through. This mass flow equals that mass flow. So this is TR1. And this is TR2. All right. And of course, as they mentioned, here's our control volume is placed around this whole thing. So these are crossing control surfaces. All right. Anything I want to do here? I guess I want to look up some stuff. So table, and we have to look up. Yeah, I'm going to get the right things here. Let's see. Let's bring this over here. I'm slow today. And my dog is nearby. Layla, how are you? All right, so we're going to go to table, what's after that one? That table B5. B5, and we'll take a look at the properties of of the refrigerant at I think it was 1 megapascal, right? So 1 megapascal right here, and 1 megapascal and 60. All right, so here, good, it's in there right there. So we want this enthalpy right in there. That's the enthalpy we want. So I'm going to write that down of table B.5.2, and at PR1 is equal to 1000 kPa, and TR1, sure, yeah, TR1, I wrote that down right. TR1 equal to 60 degrees Celsius. We have HR1 equal to I'm looking for this thing, sorry, 441. Let's see, a lot more interesting. 441.89, and these are kilojoules per kilogram. Okay, great. And we do the exit conditions too. They didn't quite tell us all the engine conditions. Well, you know what? We're going to make an assumption maybe, and exits at 0.95 and 35 degrees Celsius. So 0.95 and 35 degrees Celsius. Can I get that one? Well, let's see. Let's see what happens. They might have been nice to us. Chances are this is going to be a liquid, right? They told us it was going to be a saturated a liquid. Does it say it exits as a liquid? And so they said 35 degrees. So we see 35 degrees. No, that's not good. R134. 1 second. Let me pause. Should have already looked at this. Okay, yeah, so I know what I was doing wrong. What we want to try to do is kind of like take a look at the pressure that they were talking about. They said that the pressure is 0.95 right in here, and we could, or we could go ahead and say the temperature at 35. There you go. Temperature at 35 degrees, you can see that the pressure is 887, whereas they said it was 0.95. So it's higher pressure, therefore it's a liquid. Now the best information that we have going for us is that here's our enthalpy. Here's our enthalpy when it's a liquid. Right, so let's go ahead, and because the enthalpy is more closely associated with the temperature, let's go ahead and assume that it's going to be this liquid right here. So that's the best information that we have. And I'll write down that we had table B.5.1. All right, so it's more related to the temperature. So and then we said at T R2 equal to 35 degrees Celsius, we had P sat of that was equal to 887.6 kPa, which is less than the 950 kPa that it's at. So it's compressed more than the saturated, therefore it's like, we could call that subcooled sometimes. So we went ahead and take the H, so the HR2 we'll say is approximately HF at those conditions, which is 249.1 kilojoules per kilogram. All right. So this it ends up being an approximation. And we can also, while we're here, let's look up the properties of water. We could actually use because it remains water, it doesn't turn into steam. We could actually use a constant specific heat if we wanted to. So here's our two choices really. We go back up to steam, right? In the saturated tables right here, we can do the same thing we just did. We can try for compressed water, but most of the time the pressures are too high, and they didn't even tell us what the pressure was. So that's one of the things we had to take a look at. Let me get rid of this guy right here. It might be the one we want. What's going on here? Okay. All right. So we want to go to the temperature-based one. All right. So let me go to here. And so at the temperature-based one at 10 degrees and 20 degrees. In fact, let's actually check out what the numbers are. 10 degrees and 20 degrees. So here's 10 degrees and here's 20 degrees. So here is the fluid enthalpy. So I'm going to write this down. Table B.1.1 at T equals 10 degrees Celsius, and I'll write below it T equals 20 degrees Celsius. We have HF is equal to 41.99, and then right below it is 83.94. 83.94. Let's check out, before we move on, go back to table A1 and go into right here, into the properties of liquids, and we'll take a look at water. And water has a specific heat right here. I'll write it down, table A4. Water has a specific heat of 4.18, and these are going to be kilojoules per kilogram degree Kelvin. Kilojoules per kilogram degree Kelvin. All right, so wrote all that down. So this is going to be equal to. Oh, I should have given it units. I don't like when people don't give units for in between. You write a number down. Write some units next to it so people know. Let's go delta H right here. What is the difference between that? And that's going to be 83.99 minus 41.99. Wow, they're close. So we have a difference of 42 kilojoules per kilogram of water. But check out what if you go CP delta T? Well, the 4.18 times 10, right? 4.18 times delta T. Guess what? You get 41.8. That's not that much different. Kilojoules per kilogram. So we could have used either one of those, either looked this up for the fluid or just take Cp delta T for the water. And that's a pretty good bet most of the time to go ahead and do. So anyway, let's go back to what our process is here for a heat exchanger. I made this video longer than I meant to, but a lot of things to learn about. Coming in has to equal coming out, right? So what we're really saying is conservation of energy is going to be the heat flow rate. I go out, right? The exchange, right? So this is taking place. This heat exchange is taking place across the tubes, across the surface of the tubes, right? We're not doing any of the heat transfer stuff we did previously, where we actually had the surface of the tubes, because it's all happening inside the control volume. So we don't really care about what the mechanism exactly is. We have the inlet and we have the outlet of both of these things, and as long as this thing is insulated and there's no heat escaping anywhere, the heat that changes from this fluid has to be picked up by that fluid. We don't have to worry about what's taking place inside. So this statement is good for us, and we will just say that m dot of the water times h of the water. Now, you can start playing around with positives and negatives here if you wanted to. Most of the time, you could just know that one of the temperatures is going to go up, one of the temperatures is going to go down. So you don't have to necessarily worry about the negatives. I don't think. But the water temperature is going to go up, so I'm going to go this one minus the water temperature in, or I said the enthalpy. And I didn't really give my, maybe I got enough room. QR, well, not QR, MR. M dot R, the mass flow rate R times H R, and so this is going to be a, oh wait a minute, did I just say that wrong? I think it's going to be 2 minus 1, right? This is a 2 minus 1. It's the exit minus the entrance, right? I need to probably rewrite this. I'm going to go back to the correct equation. I have it written down on my thing. So what am I going to do? I'm going to go, it's going to be, 1 minus HR2. Okay, yeah. Another way to think of it, right? So let's go back to our big equation here. We're going to go equals Q dot, and that means Q out most of the time, minus W, and this is Q in, W in, right? Out, excuse me. We'll go out. And this is in, yeah, because this is normally a heat engine, yeah, so we're good there. And then this equation usually goes plus m dot, or they go summation of m dots. They do summation of m dots hi minus summation of m dot h e. Right. So we have no work going on across this heat exchanger, and we're going to say that it has no external heat coming in across the boundary. So all of the heat transfer is going to be these guys. So, and it's going to be equal to 0. So we'll get to the same place right here. This is a description of heat going across the internal surfaces, basically. But here is the heat that will be on the outside of the heat exchanger, which is presumably insulated. So we'll say here is going to be m dot water. All right, we don't need to call in or out, but we're going to go h water in plus m dot h refrigerant in. All right, so this should really be 1. That should be 1 for in, and then minus m dot water out. Yeah, water. But that's 2 because it's exit. That should be E. Sorry, and H water. Well, I don't need the 2 in there for that. 2, and then also minus, because it's the summation of these, right? R, I don't need a number for that, come on, R2, right? And so it should work out to be the same thing that I wrote up above. We could just gather the things around, put it onto the other side of the equal sign, and you're going to have m dot, let's go this one first, water over here, water, and then H water 2, and then this has to come back around to the other side too, so it's going to be minus m dot water H water, it's supposed to be water, 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 water 1 is going to be equal to m dot refrigerant times, and so that's going to be m refrigerant 1 minus m dot H refrigerant 2, right? Which of course turns out to be the same thing as up here. I just wanted to bring it back to this first one right there. So we know that that's true. So we can just go ahead and put the values in there. What we're trying to do is we're trying to solve for what the mass flow of the water has to be, right? So let's take the mass flow of the water and multiply it by H of the water coming out minus H of the water coming in. And so H of the water coming out is, where'd you go, baby? Oh, we have 83.94 minus 41.99, right? Which we already know that the delta was like 42. And then that's going to equal the mass flow right here of the refrigerant, which was given. Where'd you go? Mass flow, refrigerant mass flow, 0.2 kilograms per second to 0.2. And then you're going to have the enthalpy change here, which came from when it started out. That's going to be this one, right? In minus out. So in was 441. And out was as a fluid as a 249.1. Sorry about that. Okay, so my mass flow is going to be 0.9191 kilograms per second is what's required, and that's the answer to this problem. If I wanted to find the heat transfer across this, right? So bonus time. Go with some bonus material here. If you care, like bonus material here. If you wanted to find what the Q that was removed, right? So that would be the m dot refrigerant times the H refrigerant 1 minus the H refrigerant 2, right? Because we're dropping. So that would really just be the 0.2 times your 441.89 minus your 2, I can't read that now, 249.1. And this is kilograms per second times kilojoules per kilogram, so it'll be kilojoules per second is what we would end up with. So we just go 44.189 times, I have it written down, so why am I doing this? 0.1 minus, so 192.8 is how much it's going across there, and we're going to have 0.2 times that, so we get 38.56, and those are kilowatts. So that's the amount of heat that's removed. And of course, obviously you set it across this thing. So 0.9191 times this change, which is like we found 42, that also equals 38.56. So there's This is the heat removed from the refrigerant, and this, and as well, it's going to be equal to the heat that's gained by the water flow. That's enough for 25 minutes. I hope I go faster in class.